So it is with great pleasure that we present one of our new achievements, our measuring capabilities, after many years of working in the field of spring production. After good and close cooperation with the Association of the German Spring Industry, and also really close cooperation with the University of Wismar, who have been working on the subject of crack detection, cold forming, and in-process measurement technology, we have decided to launch an application this year that will provide a completely new measurement capability in the spring industry. What exactly? We want to measure the quality of cold forming and possibly also micro cracks or cracks during the production of the spring itself during the cold forming process. This is exactly what has been confirmed in the investigations and tests. How can we imagine this? One of our domains is structure-borne sound. We have been producing high-quality structure-borne sound sensors for over 20 years, which are used in the automotive industry worldwide to detect invisible cracks in cold-formed or otherwise formed components. And we do this in-line, in-process, 100%. Such a sensor, which is not particularly large, is produced by QASS itself. The sensor is screwed directly to the machine. Of course, the sensor is not screwed to the component, not to the spring, but to a machine element. Structure-borne sound has the property that it passes through all connected machine elements at high speed and at the highest frequencies. Everything the machine does is aimed at forming the spring. So all forces, all frictions, all effects are aimed at producing the spring. So what we see here, for example, the wire runs in, the wire is guided, the wire has to be cold formed, the tools make contact. Friction noises are generated and plastic forming forces are created within the wire structure. All these effects send extremely fast vibrations through the wire and through the tools. So here we can see a complete measuring chain. The only thing you need is a QASS sensor, relatively small with a diameter about the size of 25 millimeters, a measuring amplifier. The measuring device itself can be positioned further away near the machine control or wherever. You can install 1, 2, or 3 sensors in the machine, depending on what you want to scan. So you can monitor the incoming wire with the sensors, monitor the winding pins, monitor what happens at the spring itself, and of course monitor the cutting of the wire. So you get all the aspects that happen in the coiling machine with the sensor. The evaluation computer has all the interfaces you need for automation. Networks, of course, to make the data available in the company network if required, for us also to carry out remote support, PLC connections, screen connections, distinct inputs and outputs like Profibus or Profinet, completely normal 4 and 20 volt interfaces, whatever you need to automate the process. What is special about the evaluation method that we at QASS have developed and that the researchers at Wismar University of Applied Sciences have relied on? Basically, the structure-borne sound sensor works like a microphone and picks up the sound vibrations. However, the sound vibrations in the solid body are simply much faster and much more intense. What you hear outside the machine is only a small percentage of the actual information. We just hear everything. Up to 20 kilohertz, for example. Inside the machine, however, we hear something up to 20 megahertz. In other words, frequencies 1,000 times higher. And these frequencies cannot be transported by airborne sound at all. But this information is available inside the machine. Okay, the microphone records the information, but we don't stop there. We then analyze the spectra, for example, the pitches within these different vibrations, and then this image that you can see up here, where you have a normal vibration image from the microphone, becomes this much more revealing image in the spectral analysis. We then suddenly see what the friction emission looks like. We can see what the cutoff signal looks like, for example, how it changes over time, but also what pitches it takes on. And then we suddenly see that there are certain typical frequencies that contain information. Based on this frequency assignment, we can distinguish whether it comes from the winding pin, whether it comes from a drive roller, whether it comes from the spring itself, whether it has something to do with the structural faults in the wire itself, or whether a crack has just formed. In this example, you can actually see quite clearly that within this friction signal, which exists in the middle between the two cutoff signals, there is a narrow transverse signal. This is a typical stress crack pattern, where a small crack has just opened up within the spring while it is being cold formed. This crack cannot be detected at all in the normal time signal, but it can be detected in the spectral analysis. Of course, we also add different analysis methods. We place enveloping surfaces over the signals in order to evaluate exactly how the friction noise changes as a result of the tools, and we train patterns for the cracks so that you can have standard patterns to detect the crack even in such a friction noise. And the coiling process. Then we detect the one crack. If there is more than one crack, we detect that too. Within milliseconds, we have recognized the information, can report it to the machine, and the machine can sort out the springs even at a high cycle rate, or give a message that something is wrong with the material and that more attention should be paid to the quality of these springs. This structure, which resembles a landscape, suggests exactly that. The coiling process in a specific machine can also be seen as a fingerprint. Of course, one coiling process is slightly different from another, but in principle they are similar and the same. So I have such a hilly landscape, which in reality of course represents the cold forming and energy conversion in the spring coiling process. But we can train this like many other images or emissions, and then evaluate the deviations and simply describe the state of the manufacturing process. As you can see, several coiling processes have been recorded one after the other. They differ slightly, but remain similar. Nevertheless, we can also see that there may be slight deviations and anomalies at the beginning and end of the coiling process. So all aspects of the coiling process are recorded at a high frequency. Here you can see a typical evaluation of the friction noise for around 200,000 springs. And you can recognize and read off every coil change or even a tool change. You can see the trends within the wear of the tools. In other words, the entire process becomes transparent, not just in terms of the geometry of the spring, but also in terms of what actually happens during cold forming within the machine. The Wismar University of Applied Sciences has been working on other topics, which can also be seen in the research report of the Association of the Spring Industry. Here, for example, we have clear crack patterns that were recorded and recognized with our spectral analysis, which occurred during the testing of springs. Not in a coiling machine, but in a load test. But even during a continuous load test of the springs, the exact moment at which the first cracks appear can be detected. If several sensors are used, it may also be possible to see exactly where the crack has formed on the spring. And as you can see in the REM images, it is really very small cracks that can be detected using this method. Even the smallest crack generates a very clear signal in the structure-borne sound. The prerequisite is that the sensor is well coupled and can measure, but this can be done with a simple screw. This is actually a tiny crack that was detected during the coiling process. So in this case, with a size of 25 micrometers in the microscope image. And you can see another small transverse signal in the upper area, which is superimposed on the friction noise. Even this small signal can be recognized accurately with pattern recognition and our software. With this simple additional sensor in the machine, it becomes possible to monitor the coiling process 100%. You get one measured value or many measured values for each individual spring.